Perdón. Welcome all back. Thank you very much for participating then of this exercise part of the lecture of today. Thank you very much, Christina, and the space is yours.
Thank you, Esteban. Okay, so thank you for being here for the fourth tutorial. I'm gonna share my screen. Then today we're gonna start with the last part of the tutorial 3 because we didn't finish it yesterday. I would just to remind you that we have been computing the clustering of a galaxy catalog in the previous 3 workshops. In the first one, we were working with the catalog and selected the subsamples. In the second workshop, we were measuring the clustering of the sample. We did half of the work. Then we computed the DD term, which was like the hardest part actually for measuring clustering. Then in the workshop number 3, we continue working with our clustering measurements. Then we were working on the measurement or in the determination of the array RR. I have uploaded all our results from yesterday in my webpage. Then you can just download those results. We finished the workshop yesterday with the point number 7. Then I'm gonna show you what was the plot that we created yesterday. This is this one. This is the correlation function that we measured for one of the galaxy catalog. In this case, I'm using the low mass galaxy catalog. We included Poisson error bars in our measurements also, and we just checked yesterday that we actually got a power law behavior here. This is still dominated by errors because the sample is not that high. It's only 10,000 objects. Then the signal is still noisy, but you can check or you can recognize a power law shape in this plot. Then that is great. Then the last part of the workshop is actually to run the code again. Then you don't have to make new code now, just run this again, but using the other galaxy catalog, the high mass galaxy catalog in my case, to just compare with the result that we have now. Then the comparison will be very interesting, and I also put here in the number 9 some questions that I would like you to think about. Then I will do this very quickly to show you what is the plot that I'm expecting you to make, and then I will leave you to work on this and also to work on these questions, and then I will be back to discuss a little bit our results. Then here I have workshop 3. This is what we was using yesterday. Sorry that I forgot to increase the size of this. This is a bit annoying. Give me some minutes. Okay. Okay, I think that is enough. I guess just a little bit more. Okay, this is just the code that we finished yesterday. I uploaded this code in my webpage too. Then this code just read the catalogs, the random, the high, and the low catalog. We defined the clustering parameters. We create DD. And then we create at RR, which is just exactly the same code as DD, but you just have to change the coordinates here and use the random positions that we have. Then this code already make all the job. We normalized the estimator and we add error bars here. Then we did all of that yesterday, step by step. Then now I'm gonna create the DD2. I will call this for the high mass sample. Then this is just copy the code that we have here. Then I'm gonna just copy what we did yesterday. Then for DD is this part of the code. Then I'm gonna put this here. Then I will call this DD2. The number of sources is the one corresponding to the high mass catalog. Then here I just have to change the number of the variables. Then this is the total number of sources. Then here, instead of the coordinated of the low catalog, I have to use the high catalog. Simply. And that's it. And and we have to here store this in the DD2 array. And that's it. This is just a copy paste. And now I'm gonna copy the part in which I compute the estimator. And that is, where is that? This is RR here. I have to normalize again my data. Then this is DD2. Compute omega, and here I'm using the same random catalog as I said before. This will be omega H, DD2, RR will be the same. I will add error bars now in the same way as before. Normalize 2. This is 2 error omega high. Okay, I just copy everything. And then I'm gonna open this to make the plot. Then I have that part of the code just here. Yes. Okay, so I'm gonna plot the same as before. Actually, I'm gonna copy this plot. I called this angular correlation function both. Then there is the one that we compute before. Here I'm gonna plot the error bar for the first one. And then I'm gonna plot also this for the new one, which is here omega H, error on omega H. And I will plot this in red. Okay, then I think we are done. I'm gonna run this code and hopefully this will work. Then now we should have the clustering measurement for both catalogs. Then you can see that you already had most of the work and you can provide any Galaxy catalog that you want. You can already measure the correlation function, the angular correlation function for any catalog. And this take a little bit to compute the distances. And now I'm gonna show you what is the plot that I expect you to obtain. This one, both. Okay, this is the result. Then here in black, I'm plotting the correlation function for the low mass galaxy catalog, and in red, I'm plotting the correlation function for the high mass galaxy catalog. Then you can see that the red points also follow more or less a power law, and we have a very different result in terms of clustering with the other catalog. Then that is nice. And I will give you now 10 minutes for you to make this plot. You have to just run your code, and please try to think a little bit on the questions that I suggest in the workshop number 3, the question 9. These are the questions. Then I will give you some minutes, and I will be back in 10 minutes, and we'll discuss the answers of all those questions. Then I'm gonna stop sharing, and I'm gonna be here. Then in case you have any question or anything, please let me know. Then I will be back in a while. Okay, I'm back now, and I hope you could finish your plots and you could reproduce what I just showed you. Okay. Then those are the questions that I propose you to discuss. And here I'm going to show the plot. Then again, here red is the correlation function for the high mass sample, and black is the correlation function for the low mass sample. Then I first ask is if the correlation functions are different. Then clearly they are. Red points are all of them systematically very well above of the black points, which means that that population is more clustered than the other. And if you remember from the first tutorial, when we plot, I can show you that actually, when we plot the distribution in the sky for both samples, I asked you to determine if you could say that one population is more clustered than the other, just looking at the sky distribution. Then this is, for example, the sky distribution for the low mass sample, and this is the sky distribution for the high mass sample. And just by eye, at least I cannot distinguish any different pattern here, like in which I could say which population is more clustered than the other. However, if we describe the distribution mathematically using the 2-point correlation function, we can see a really important difference. Then that is to show you that this mathematically way to measure the distribution of sources is very informative and is working well. Okay, which is higher? We already said that. Which population is more clustered? I already said that higher clustering, a higher 2-point correlation functions means a higher clustering. In this case, we are comparing two samples over the same redshift range. Then we can directly compare the correlation function between them. I recall that we are measuring the omega theta. This is the angular correlation function. We are integrating over the line of sight, but only between redshift 1 and 1.5, because we selected our galaxies only in that range. Then it's not a large range, and that means that the clustering signal is not being diluted that much. And the other important point is that both both samples has very similar redshift distribution, as we show with the plot in the first tutorial. This was the redshift distribution for both samples. Then we can assume that the redshift distribution are very similar. Then if we will make an attempt to translate this angular correlation function into a 3D correlation function in which we have to use the Limber equation, the result will still be the same, like red points will have a higher clustering because this depends more on the redshift distribution of the sources, and in this case the redshift distribution is the same. Then that is why we can make the statement about the clustering, the 3D clustering of the population just based on the angular correlation function. Then what does it imply? Well, this implies that high mass galaxies reside in more massive dark matter halos. That is, also, were you expecting the result? Yes, that is obvious, because by construction, we choose the red sample here to be composed by the most massive dark matter halos in the simulation. Then by construction, we choose this sample to be more clustered and more massive. Then that is exactly what we are looking in this measurement. Then that is nice that we confirm that we are measuring what we were expecting. And the last question is, how are the error bars compared between the samples? This is a very interesting question because if you remember well, both samples contained similar amount of galaxies. Both of them had around 10,000 galaxies. Then in principle, if the error bar is just Poisson, then we will expect that the error bar for both correlation functions should be very similar. However, here we can see that the correlation function for the red points in general has slower or smaller error bars in all the beams. And the measurement for the low mass galaxies is more noisy. And this is just to show you that the size of error bars depends on Poisson, depends on the number sources that you have, but also depends on the intrinsic cluster or the intrinsic clustering of the sample. Then if the sample is more strongly clustered, as the case of the red points here, you're gonna have more close pairs for this sample compared with the black one, because it's just more clustered, then everything is more grouped. Then when you count the number pairs at these beams at really small scales, you will have more points concentrated, and then you're counting more number of pairs in the same beam compared with what you will obtain in this other sample, which is less clustered. Then in other words, if the sample if we have a population which is strongly clustered in the universe, we don't actually need a super large survey, because we anyway will have a lot of pairs at small scales. Then if we just want to measure the clustering at small scales, a strong intrinsic clustering will allow us to work with not that large catalog, and we will still have a good signal to noise for the measurement. Then that is the main point that I wanted to make with this question here. Okay, so that was the last part of workshop 3. And now we're gonna work in workshop number 4. You already received the email with the instructions for this workshop, but I'm gonna read it anyway. The idea is to now we will make a check for our codes, because as I already mentioned in one of the lectures, if you cross-correlate two random catalogs with both of them, with randomly distributed sources in both of them, then no clustering signal at all, then we should obtain a correlation function equal to 0 at all the scales. And that is actually a very good way in which you can check and test that your code is working. If you don't get 0 at all the scales when you use two random catalogs, then something is not working in your code. Then just to check that and to check that you are getting 0 clustering in this case, I propose you to just run your code, the code that just created, and see the plot. Then I'm gonna work on that now. And after that, the other part of the workshop today is to just use a different estimator for the correlation function of the samples that we just measured. Now we just use the simple estimator, but as I told you, the most used estimator is actually the Langley-Shalai, which handle better the edge effect, for example. Then this should give us a better answer for the clustering. Then the idea is that we could compare both the simple estimator and the Langley-Shalai estimator. Then I'm gonna start with the random catalog, with the clustering of 2 random catalogs. Then I'm gonna show you how to do this, and then we'll give you some time for you to work on this, or you can work together with me also. Then the first step is to create a random catalog and call it random2. And for that, I can just use the code from the workshop number 1. Then I also need to use what we had in workshop 3. Then I'm gonna copy this code and put here in workshop, no, not here, in workshop 4. Then this is gonna be my new code now. This is just the code that I use for workshop 3. Then, okay, this is all my code. And now that we finish here, I'm gonna compute the correlation function for 2 randoms. Then first I'm gonna create a random. Then I'm gonna use the code from workshop 2. I have this one here. Yes, then I'm just copying this from the first workshop, the second workshop. Then I'm using the same minimum and maximum values as before. I'm gonna call this R2. This is my second random catalog, and then this will be random2 dot, and I'm gonna print the new positions here. Okay, and that is all. I'm just gonna run this once at the end because otherwise it will take so long. I have my second random catalog. Then I'm just have to use this random2 dot catalog as my data catalog, and my other random catalog, the same that we used before, as a random catalog, and run the code and plot the correlation function. Then that is just run the code, the same code that we had. Then I will actually create this random catalog here in the beginning of my code. Then I can just, this code already compute the correlation function for the data. Then the only thing that I'm gonna do here is just to say that this is the coordinates for the data. I'm just gonna replace the coordinates by the coordinate of the random that I just created. Then this is random2, and this will be the random2. Then I'm just changing the name of the variables. Then the input catalog instead of the data will be the random. That is all the thing that I'm doing. And yeah, and I'm done. Then I have to just run this. I will just avoid to create again this R plot because I'm not interested on that now. And I just want, yeah, let me check. This is the angular correlation function plot. And I will stop here because I don't want to run using my second data catalog. Then this, I'm gonna call this random. This plot should contain the plot that I want. And the other change that I'm gonna do here is that the y-axis of the plot need to be more close to 0. Then I'm gonna put here from 0.2 up to 0.2, and the plot cannot be logarithmic in the y-axis because we will obtain hopefully only 0 values. Then that is all. I'm gonna run this code now. And let's see if this works. I'm just running my code with different catalogs. Okay. Then I'm gonna check in workshop 4 results is this one. Yes, I think it should be this one. Yeah. Okay, this is the plot that I got. You can see that I have, well, more or less everything at 0, but we still have some variations, but at least we don't have like a strong power law as in the case of the data. And this small variation could be just because the random catalogs are not large enough. But if I generate several times different random catalogs and compute this several times and then average the results, I should obtain exactly 0 over all the scales. Okay, then that is the only reason why this point is going up and this point is going down a little bit. Then you can see also that the error bars is still large. Then you can also try to run your code and see if you have something more close to 0. And you can also try running with different random catalogs and check if you get 0 at all the scales. Okay, then I'm gonna give you some time now. Then you can reproduce what we just did. I'm gonna stop sharing. And what time is it? Yeah, I'm gonna give you 10 more minutes then, and after that I think that it's time for the break. Then I'm gonna be back in 10 more minutes, and then we can decide what to do. Okay. You had already 10 minutes to finish this part. Then it would be nice if you can let me know if you were successful in creating, in having a clustering of 0 at all the scales using the 2 random catalogs. That would be nice. And if you can send me the plots by email, it will be also very nice to check that you are getting the results correctly. And yes, now the second part of the workshop is to compute a different estimator, the Landley-Salai estimator. Then I think that we could make the break now because we are 10 minutes ahead anyway. Then maybe we can make a break of 15 minutes and continue with the second part after the break. I think that is better. Then, Esteban, are you there?
Yes, Christina, thank you very much. Then we should reconvene. So it's 15 minutes. So at 11:20, our time will be 5:20 your time.
Yes, that is better.
Okay, perfect. Then see you in a couple of minutes.